Okay. So there are going to be two things we're talking about here in this little spiel. One is, to kind of tie together all the things we've been talking about in terms of landforms and interpreting those landforms in terms of the water cycle. But there's a lot of interesting data also on the mineralogy of Mars that reinforces and kind of tweaks this story. So I want to bring those in as well. So again, basic ages of Mars based on crater counts and landforms and so forth. We've got the Noachian as the earliest times on Mars, the Hesperian is the Middle Ages of Mars, and we're currently in the Amazonian. And Amazonian is what we'll talk about after break. Cold, dry, dusty Mars. And so again, to what extent was early Mars warm and wet? So the valley networks were evidence. We interpreted the valley networks as what? This is review, people.
Can you repeat that again?
What did we interpret the valley network systems as being representative of?
Like channels that transfer water.
Okay, so we talked about them being essentially fossil river systems. We talked about this hypothesis that Mars had an ocean in the past. Here's a more artistic rendering of what that might have looked like, or what it might look like once we get done with the planet in the future. So, how might this have changed over time? So I want to go through this diagram in a little bit of detail, and we'll come back to this diagram maybe a couple of times during this little wrap-up. So, if what we're talking about with a warm, wet early Mars is the case, then early Mars would have had a hydrological cycle like the Earth's. It would have had an ocean that might likely have been ice covered. So the ocean would have been a major reservoir of water, and even with the ice cover, we're going to get evaporation off of the ocean. We're going to get precipitation on the ocean and on the land, and snow at the poles, and valley network systems would carry that water downstream. There would also be Mars is never going to be really, really warm, so there's always going to be some layers of buried ice in the upper levels of the soil. And down at depth, there's presumably going to be pockets of water, groundwater, that forms its own pathway of water moving through this. So we've got this kind of conveyor belt of water. Couple of different mechanisms for that water returning to the ocean, and then the ocean returning water to the atmosphere to keep this cycle going. Over time, as Mars gets colder and colder, the ice on the ocean is going to get thicker and thicker. The cryosphere, which is this layer of frozen soil that kind of seals the upper layers of the soil, is going to get thicker and thicker. That's going to reduce the action of the valley network systems. There's going to be more of the precipitation is going to fall as snow at the poles, and so more of the water is going to be entering the groundwater system, because that polar ice cap, you're going to get melting at the bottom of the polar ice cap, and that water is not going to flow across the surface in valley networks, but it's going to trickle down into the groundwater. It's going to move through this subterranean route back to the ocean. And as this continues, the ocean eventually is going to get completely kind of sealed off from the atmosphere, building up a large icy crust. The groundwater system is going to get more and more extensive. The water table is going to eventually build up under this frozen cap of ice. And this difference in water height between what's going on with the groundwater and what's going on with the ocean is going to lead to a big high pressure system. This is kind of similar to why we build hydroelectric dams, to raise the water level so that there's a higher water pressure for running the turbines. So what we might expect to happen out after that builds up more and more is that periodically this cap that's holding back the water that is building up underground fails for one reason or another. You know, it could be that there's a meteor strike, or it could be just the pressure builds up so much. And once this cap breaks, we're going to have cubic kilometers, essentially, of water rushing out across the landscape. And then by the time we get to present-day Mars, much of the water has been sequestered or disappeared in different areas, and we have no real evidence for an ocean anymore. And we get the kind of dry, dusty, cold Mars that we see today with this huge, thick layer of cryosphere frozen material. Okay. That's a nice story, or hopefully you think it's a nice story.
So is there proof of any underground water?
Yeah, we are looking for underground water today primarily through radar instruments on a couple of the missions. And there's evidence for underground water from some of those radar signatures. We clearly don't have drilling rigs on Mars yet. So, you know, once humans get to Mars and want to do research, one of the big things we're going to want to do is drill, just to see what's going on in reality down below the surface there. But I do want to say that, you know, this phenomenon of the aquifers periodically bursting and pouring water out across the landscape that we haven't talked about much yet, which are these outflow channels. And actually I could have picked a couple better pictures than this, but even back in the Mariner 9 and Viking missions, from orbit we saw these parts of the landscape where it looks like, you know, the land just kind of fell apart, and then downstream from there are all these scoured features where you've got, you know, where it looks like there's clearly evidence of large, massive flows of water just going across the landscape, scouring away everything in its path. Here is a crater that provided a little bit of obstacle, and you can see that the water was rushing from the lower part of this figure to the top, and as that water rushed around, it flattened and heavily eroded all of the material in its path. So these are really truly massive floods. The valley network systems are fairly narrow channels, they're highly branched. These are wide, massive, pretty much unbranched channels that cut a huge gouge into the landscape until the water eventually peters out and you get this kind of braided network structure at the end where the water is kind of meandering after it has after it's spent all of its kinetic energy. The valley networks are typically clustered in the southern highlands, the oldest terrain on Mars. These outflow channels instead are found specifically where you've got big difference in elevation between the highlands and the lowlands, like the water has burst out and it has run downhill into either the northern lowlands or here into Hellas Basin or various other structures like this. So these were truly catastrophic events. It would be bad to be in the path of one of these, but these are all mostly dating to Hesperian, that kind of middle time frame of Mars when Mars was drying up. And we tend not to see many of them in more recent terrain. Okay, so yeah, I think I've covered everything here. But we get this, basically, we get this change from what we might consider a cool, moist kind of Mars in the Noachian to this hydrologically, sporadically active area in the Hesperian. And then the current Amazonian is kind of dry and dusty. Okay. So, just quickly, this has been reinforced a lot over the last few years in terms of the minerals that are being found that are associated with these different time periods. There are two important spectrometers that are looking at these mineral signatures from orbit. There's the Omega instrument on the Mars Express and XRISM on the Mars Reconnaissance Orbiter. By looking at the infrared wavelengths of light, they can differentiate different kinds of minerals. So a phyllosilicate clay would have a different kind of signature than a sulfate deposit. And so these instruments from orbit can identify outcrops of these different kinds of minerals. Clays are interesting because they represent neutral water. Anywhere you find clays being laid down, those are areas that would have been much more benign. Sulfate deposits, like what Opportunity found initially in Meridiani Planum, would have represented more acidic conditions. Okay, with that. But these instruments not only can identify these minerals, but they can identify them in very fine spatial distribution. So here is a mola elevation figure from an area called Marwath Vallis. And this is the signature specifically for some of these clays. And from orbit, the instruments can identify where specifically those clays are found in relationship to the surrounding structures that are identified by the cameras and the mola elevation data. So, coming out of this is this new framework that I want to make sure you're introduced to. So as opposed to these ages of Mars based on crater counts and landforms, these new results are indicating three primary environments based on the kinds of minerals that are laid down in those different time periods. So this Phyllosian era is again an era of clays. So this would indicate widespread water that is neutral, very habitable environment. We know that there's a lot of volcanic activity separating the Noachian from the Hesperian. That's probably what resulted in this heavy production of sulfates and other salt-related minerals. In the Theakian era, so this would represent that time period when Mars is drying out, the bodies of water are getting more acidic, they're getting more salty, they're evaporating, they're leaving these extensive salt deposits, and then that goes into the modern era of Mars where we have very little evidence of widespread water activity in terms of producing the kinds of mineral structures. And so we have instead more of a focus on these anhydrous ferric oxides, which don't really indicate a habitable environment in the way we think about them. One of the reasons for sending Curiosity to Gale Crater is that this Mount Sharp peak in the middle of Gale Crater hopefully will represent that whole mineral history. From looking at orbit, it looks like the lower layers down here, and this is a gross simplification, have a lot of those phyllosilicate clays, which was what we would expect if they were laid down during this benign, early, warm-ish, wet environment. And then there's a clear transition to upper layers that are more dominated by the sulfates, indicating Mars crapping out, getting less and less habitable all the time. And then, although opportunity may not actually get to the top of Mount Sharp, these higher elevation strata are clearly going to be all Amazonian deposits that really are not laid down in a water-rich environment at all. How am I doing?
It's time.
Perfect.